So now we're moving on to part 5 of our loose end series. We've looked at what it means to solve a quadratic, the ways to solve a quadratic. We looked at the discriminant to determine the possible types of solutions. Then we went through rational solutions by factoring, and now we're going to do real solutions by using the quadratic formula. First thing we're going to do is start out with a review of simplifying radicals, because it's important to be able to simplify radicals when you're getting more in depth with your solutions to quadratics. So as we look at a reminder of how to simplify radicals, we're just going to take a couple of examples. So the first step when you want to simplify, say the square root of 50, is you break the radicand, the number underneath the radical, apart using the greatest perfect square or using a series of perfect squares. Either way, it works just fine. Here's a list of the perfect squares over on the right, so we can use that as a reference. We can break the square root of 50 up into be the product of the square root of 25 times the square root of 2. We could have broken that up into the square root of 10 times the square root of 5, but that's not helpful because neither of those is a perfect square. So you always want to break it up into a perfect square if possible. And then the square root of 25 is 5, and the square root of 2 does not simplify any further, so it's simply just the square root of 2. So the square root of 50 simplifies to be the 5 times the square root of 2. Then we move to another example, the square root of 40. We're just going to break this up into the square root of 4 times the square root of 11. Again, we could have broken it up into 2 and 22, but that's not helpful because it's no perfect square. So you always want to use a perfect square. Then underneath, the only difference between this one and the one on the left that we just did, the square root of 50, is that this is negative 50, the square root of negative 50. So we just have to use the imaginary unit to represent our square root of negative 1. So that negative essentially just comes out from underneath the radical as an I, because the square root of negative 1 is I. And then the square root of 25 we already know is 5, and then the square root of 2 stays because it's an irrational number, so we can't simplify it any further. And then by the same token, this is simply 2 times the square root of 11 with the I pulled out because of that negative underneath. So here we're going to look at simplifying radicals. And again, we've got the list of perfect squares here. I'm just going to slide it over so it's on the left. And then we're going to rewrite 72 using perfect squares. So there's a couple of ways you can do this. I'm going to just go ahead and start dividing by perfect squares. So I know that 9 will go into 72 8 times. 9's a perfect square. And then 4 will go into 8. 4 is a perfect square. So 4 goes into 8 2 times. So then I can rewrite the square root of 72 as the square root of 9 times 4, which is 36, times 2. Or if you need to write it out as 9 times 4 times 2, and then you can think of it as the square root of 9 times the square root of 4 times the square root of 2, and then that becomes 3 times 2 times the square root of 2, which is 6 root 2. Now we're going to go to the next one, which is the square root of 81. It's always a good idea to keep these square roots in your mind, to just kind of memorize all the way up through the square root of 225. Because 81 is a perfect square. So 81, the square root of 81 is 9. So there's no simplifying that needs to be done. That's a perfect square. You can take the square root of 81 and get 9. So just be aware that you've got those perfect square options. Not every single radical is going to need to be simplified in a complex way. Sometimes it's very straightforward. Square root of 175. I know that 175 is divisible by 25, so I'm going to rewrite it as 25 times 7. Then I break it apart into 2 separate radicals, the square root of 25 times the square root of 7, which becomes 5 times the square root of 7. Moving on to 9 times the square root of 245. No, I guess we're going to go to 600 next. So the square root of 600 I can write as the square root of 100 times 6, And then the square root of 100 is 10, so that becomes 10 times the square root of 6. And then 5 times the square root of 180. Again, I can break 180 down. I know that 9 will go into it. 9 goes into it 20 times. 4 is a perfect square. 4 will go into 25 times. So then I know I can write this as 9 times 4 times 5. The square root of 9 is 3. The square root of 4 is 2. And then the square root of 5 doesn't simplify. So then that ends up giving me 30 times the square root of 5. So 5 times the square root of 180 simplifies to be 30 times the square root of 5. And then finally, 9 times the square root of 245. I recognize that 5 will go into 245. So 5 goes into 245 not 81 times. 5 goes into 245 49 times. 49 is a perfect square. 7 times 7. So I'm going to rewrite the square root of 245 as 9 times 49 times 5. And then that becomes 9 times the square root of 49 times the square root of 5, which is 63 times the square root of 5. So now let's take what we've done here with simplifying radicals and carry it into this next problem. Now, this one is not going to work out as I had intended it to, but we're going to go ahead and include it. This is actually going to come out to be a non-real solution, but it's here, and we might as well look at it because it will help us see the parallel and the difference between the two. So I'm going to go ahead and get this in standard form and work through the quadratic formula, identifying a, b, and c, all values of 1. And then I simply evaluate and simplify, and I get -1 plus or minus the square root of -3 over 2. And this is where, at this point, we realize that the discriminant, the thing that we talked about a couple of videos ago, is a negative number. So at this point, you recognize that this is going to be a non-real solution. It's got two solutions. One is a -1 plus I root 3 and 1 over 2, and 1 minus I root 3 over 2. Just remember that square root of -1 we can replace with the constant I, the value I. So our two solutions are -1 plus I root 3 over 2 and -1 minus I root 3 over 2. And those are non-real solutions. They are not real solutions. This next one is going to have real solutions. So the first thing we need to do is get it in standard form. So we want to add 4x to both sides and subtract 37 from both sides. So we get 8x squared plus 4x minus 37 equals 0. Then we identify a, b, and c. And we use the quadratic formula. Our b is 4. A is 8 and c is -37. And then we do it in 4 parts. So -4 plus or minus the square root of 16 minus, and then I'm going to multiply -4 times 8 times -37. And that's 1184. All of that is over 16. And then when I add 1184 plus 16, that becomes 1200. So I have negative 4 plus or minus the square root of 1200 all over 16. And then I can simplify that radical 1200. I know that that's equal to 12 times 100. And I chose 100 because that's a perfect square. And then I'm going to rewrite 12 as 4 times 3 because 4 is a perfect square. So I'm just breaking that up into as many perfect square factors as I can. And the square root of 3 does not simplify, but the square root of 4 is 2, and the square root of 100 is 10. So the square root of 1200 simplifies to be 20 times the square root of 3. So then I replace that square root of 1200 with 20 times the square root of 3 over 16. And then I recognize that all 3 of those terms in that fraction are divisible by 4. So I'm going to take the negative 4, and divide it by 4, and that gives me 1. And then I'm going to take the 20 and divide it by, so it gives me negative 1. 20 divided by 4 is 5. 16 divided by 4 is 4. So my two solutions are negative 1 plus 5 root 3 over 4 and negative 1 minus 5 root 3 over 4. And it's always a good idea to check this. Graphically, so that you can see that your two solutions actually are, that your algebraic solution matches up with your graphical solution. So I'm just going to go ahead and graph this quadratic, 8x squared plus 4x minus 37, and then I'm going to compare the two x-intercepts with the two simplified answers to make sure that I'm correct. You can do this with real solutions, with rational solutions. You cannot do this with imaginary solutions because you can't see the imaginary or non-real solutions. So you can see there that one of my solutions is 1.91506, which is what negative 1 plus gives us. Negative 1 minus gives us negative 2.41506. And so I can rest assured that my algebra is sound because it agrees with my graphical solution.